This section is on reaction rates. Rates of reaction can be determined by monitoring the change in concentration of either reactants or products as a function of time. So here you can see at time 0 seconds, in the reaction vessel, we have 1 mole of substance A. As time progresses at 20 seconds, we see that some of A is now B. We have half a mole of each. And then at 40 seconds, we have more of B and less of A. So we can say maybe that substance A is our reactant, and as the reaction proceeds forward, we see more formation of product, okay? And the rate of the reaction is determined by just monitoring how quickly the product is formed or how quickly the reactant is used up. In this reaction, the concentration of butyl chloride, which is this reactant right here, was measured at various times. So you can see here as time increases in seconds, what happens to the concentration, the molarity, you can see it decreases, right? So as that reactant is used up, you see the concentration decrease with time. After you've measured the concentration of the butyl chloride over a period of time, you can find the average rate of reaction over each time interval by just finding the change in concentration in a given time interval divided by the change in time. So here, for this first time interval, we find the difference here, the change in concentration, over the time interval of 50 seconds to find an average rate of reaction that would be 1.9 times 10 to the minus fourth, and that would be molarity per second. Look at this column that's circled here at the average rate of reaction. What do you see happens to the average rate as the reaction proceeds? It starts out at 1.9 times 10 to the minus fourth molarity per second and ends at 0.560 times 10 to the minus fourth. So we can say that over time, the rate decreases. What if I take that same concentration over time data and I plot it on a graph? So on the y-axis, I have the concentration of my reactant, and on the x-axis, I have time, okay? And so the rate is the change in concentration with respect to time, and you can see that rate decreasing as time goes forward, okay? So a slope that, so it says here, what do you think the slope of the line tangent to the curve at any point represents? Well, we have the answer right here. You can see, maybe with a yellow pen, you can see this tangent line that's drawn right here, tangent to the curve, and we're told that that's the instantaneous rate at time equals 0 seconds. And later at 600 seconds, there's a little line drawn here you can see, and that is the instantaneous rate at time equals 600 seconds. So we can find the instantaneous rate of the reaction at any point in time by just drawing a line that's tangent to the curve. Just as we see with this curve, do you see the rate here decreases over time? All reactions slow down over time. Therefore, the best indicator of the rate of a reaction is the instantaneous rate near the beginning of the reaction. In this reaction, the ratio of butyl chloride to butanol is 1:1. Therefore, the rate of disappearance of butyl chloride is the same as the rate of appearance of butanol. So we can say that the rate is equal to, so we have the rate is equal to the change in concentration of the butyl chloride over time, which is equal to the rate of appearance of the butanol, or the change in concentration for the butanol with respect to time. Now we have this question though, why is there a minus sign here in front of the butyl chloride? Well, of course, that's because the concentration of the butyl chloride is becoming less as the butanol becomes greater. So the negative sign indicates the disappearance of butyl chloride. The rate of disappearance is equal to the rate of appearance of butanol. What if the ratio is not 1:1? So here I have a reaction that has 2 moles of HI, to produce 1 mole of H2 and 1 mole of I2. For every 1 mole of I2 that is produced, 2 moles of HI must decompose. So the rate of disappearance of HI is twice as fast as the rate as the appearance of I2 or the appearance of H2. And so we indicate that by this this coefficient here. It's 1 over the stoichiometric coefficient because we have a 2 here. So to generalize for any reaction given stoichiometric coefficients lowercase a, b, c, or d for reactants and products capital A, B, C, and D, the rate is equal to, we have a minus sign of course for the reactants because they will disappear, and it's 1 over the coefficient times the concentration over time, minus 1 over B times the concentration over time equals 1 over C times the concentration over time equals 1 over D times the concentration over time.